It is the most interesting chapter where we will find out whether in the reaction medium or in intermediate there is any free radical or not. Free radical or free electrons, free radicals present or not. That's how we would find out. Okay. This is the importance of HBr spectroscopy. So let's find out. Rotates on its own axis, it generates a spin angular quantum number, and that is the half. Okay, and the momentum, spin angular momentum it generates. So in quantum mechanics, the formula is now we designate it as total spin angular momentum is equal to this h card. Okay, h card is h by 2 pi. Okay, this is actually h by 2 pi. Okay, this is the spin quantum number is. Now we can know. Now there is an interesting thing that this spinning motion that it is rotating in an orbit. Okay, rotating in an orbit. Now see which orientation it will take. Now suppose if we apply a magnetic field. Okay, we apply a magnetic field. Now suppose this is a orbit. Okay, so in which orientation it will take? So suppose these are the orbits. This is the positive z-axis and this is the negative z-axis. Just for consideration, we are taking this. Now see, now here is the electron. So it is rotating. So which orientation it will take? So this is the spin angular momentum. This and this is suppose is z. Okay, this is z along z-axis. So we name this as Sz. Now quantum mechanics says which orientation it will take. Now actually when we apply the magnetic field, the component that is coming in the z-axis, that will be the half integral. That is the half integral value. Like those orientation it will adopt. Just let me clear. Okay. So S bar we know this value. So Sz will be how much? Sz will be the half integral. Okay, it will be the half integral. It may be positive or it may be negative, doesn't matter. It will be the half integral. Okay. Now if we apply this consider here, so if this is the theta, okay, this is the theta, then we can know that is the because Sz have only two values. Okay, Sz have two values because Sz have this is the formula of Sz. This is a spin quantum number. Okay, so it has two values. So Sz have two values. So S can have only two orientation. So according to the definition, so S bar cos theta equal to Sz, isn't it? Because this is a if you apply that formula, you can understand. The cos theta is the like the base is z, so cos theta is z. The electron is rotating, and we apply a magnetic field, so it behaves a tiny magnet. As it behaves a tiny magnet, so it should have a dipole moment vector, and this is Landé G factor. Okay, Landé G factor. Okay, and this is the mass of the electron and this is the charge, and this is the total angular momentum. Okay, now magnetic moment vector will work opposite. Okay, understood? So S and mu will opposite to each other. That's why we get the negative sign. Okay, okay. As the electron is spinning here, so it should have associated with the energy. The energy is now the magnetic moment vector is this and the applied field is this. So how much the energy gained is? This is the fact. So now mu z is nothing but the mu cos theta. Okay, understood? And this put the formula here. That formula of mu. Okay, dj. and we know what is S cos theta. G is by 2m Sz Bj, and we know Sz equal to ms h cut. Right? Just as easy as that. Sz is the ms h cut. Finally, E becomes G mu b Bj ms. Okay. Now, so E has two values. That is a plus half B this and minus half G. Now see, as we apply the magnetic field, so some electron will align along this direction and some electron will be opposing this direction. So those are opposing, those will be high in energy, so they have the high energy value plus, and those are aligned, they will be low energy value this. So if I talking about the simple one electron system like hydrogen, so this is the delta E. So delta E becomes G mu B Vj, just minus rotating, and there is and in a orbital as centering to nucleus. So nucleus is also have a magnetic quantum number, that is the represented by mi. And when this magnetic quantum number coupled with this magnetic moment of the electron, then that gives to a hyperfine spectra. So this line will split again. So let's take the hyperfine splitting constant as A. So the total energy of hyperfine splitting will be extra A mine into ms. Okay. The total energy associated will be G mu B B mine ms. Nucleus has a have their unique property, like the amine have some values, maybe half, maybe 1, maybe 3 by 2, maybe 5 by 2. So these may have. So this magnetic quantum number of the nucleus, that is already there. So for every spinning motion there will be the magnetic quantum number ranging from -1 minus I to plus I. Okay. For every spinning quantum number, there are magnetic quantum number of nucleus minus I to plus I. Okay. If you consider the normal case for half, so it will have minus half, so A mine will have minus half and plus half. So this is already there, so this factor you have to write. Now the lowering energy means it should have the negative value. It is already negative, so more negative will be the lowering in energy. So ms is already have negative half value, so I should take the positive of half, means half into half. Understood now? So it is nothing but the minus a by 4. So it have plus, so it have minus g mu b, and this will be positive wave. It is the highest in energy. So suppose this is E1, E2, E3, E4. Understood? So if we write these things, this is the ms, this is the mi. Okay. Okay. Now there is a selection rule, that is for transition. M is equal to plus minus 1 and eta m equal to 0. Now there is a significance of it. So according to Frank-Cohen principle, what he had said, like during the electronic transition, it is so rapid. The electronic transition is so rapid that during this transition there is no movement of nucleus at all. So what it means? So this is the spin magnetic quantum number is changing. So means spin quantum number will change, but the magnetic quantum number nucleus will not change. That is nothing but the Frank-Cohen principle. Understood? Number will change to plus minus 1. So from this we can jump from here, and this will be half. So only possibility is there, and here only possibility here, because this will be the same, should be the same, and for this it should be the same, and this is the plus minus 1. So only two transition can be possible here. Then mi has value -1, 0, 1. These are the values of mi corresponding to any ms. So from here to place there, from here the transition can take place there, and here to here. Okay. So only three transition can take place. Now see, there is another nucleus also. Okay. Now there is another nucleus. Actually, the electron is sharing by the two nucleus. So this nucleus will also have the effect as of like that. So suppose this has hyperfine splitting constant A1 have A2. Okay. This have Mi1 or Mi2. Understood? Okay. So what will be the energy? Energy will be the G mu B Bj Ms plus A1 Mi1 Ms plus A2 Mi2 Ms. So these 8 energy levels will form. Now the transition is like that: delta Mi1 equal to 0, delta Mi2 equal to 0, delta Ms equal to plus minus 1. Understood? This is our the standard condition for the transition. Okay. Now delta Mi should be plus minus 1. Okay. Now you can see, so this have the same value of this. The first transition will be there, and this find out there. Second transition will be here. Third, it will be here. Fourth, it will be here. Okay. So four transitions are possible. So if we apply this for this one, so the energy comes like for this level. For this level, if we apply this energy value, then the value comes, we calculate the energy of transition. So we have to subtract the value of higher level to lower level. The energy of transition we calculated like subtracting from upper to lower level, okay, by putting this formula. Understood? Now there is interesting fact. So this is the hyperfine splitting constant, and we have taken like A1 not equal to A2. Now see, if A1 not equal to A2, then four transition are there. Okay, four transition, and they have the intensity 1:1:1:1. Okay. Now see, if A1 becomes equals to A2, suppose both are the hydrogen, okay, and they are in the same environment, then what happens? Then A1 becomes equals to A2. So this will vanish 0, and this will vanish. So this E2 and E3 will be same. So the thing is that E2 becomes equals to E3. So actually these two transitions become same, but the intensity doubles. Okay. So the ratio will be, so only three transition will appear, but the ratio will be 1:2:1. Understood now? So these two are equal. Okay. So they gives rise to the higher intensity. Hydrogen. Okay. So we got two transitions. When there are two hydrogen with the same environment, we got three transition. So here the intensity ratio are 1:1. Here the 1:2:1. So similarly, if we apply three hydrogen and then by do it by yourself, then four transition will appear, and the intensity ratio will be 1:3:3:3:1. Okay, the intensity ratio will be 1:3:3:1. Okay, so you can see this is like a triangle. It's forming. 1:1. So this is called Pascal's triangle. Okay, what this is called? Pascal's triangle. Okay, so it has a formula also. Like the formula of getting the number of hyperfine line is that 2ni plus 1. So 2ni plus 1 means, so n is the number of EPR active nuclei. Okay, and I is the, the nuclear magnetic quantum number. That is for only one case. Suppose if there are four hydrogen, two hydrogen, so we can apply here. But if there are two different nuclei having the different environment, then the law will change. So just like probability, like you see, if in each case of A2, A1 will split again. So number of lines will multiply with that. So if suppose in one number of nucleoactive nuclei and having the nucleoactive one, so the total number will be 2 I2. This is the total number of signal for the N1 N2 nuclei having I1 and I2 nuclear magnetic quantum number respectively. Okay. Now if have ith component, so the overall equation will be pi I. Pi is using to you to like the products. Okay. So 2 ni plus. So these are the number of lines. The formula. Okay. Just 3 by 2. So the thing is that if there are no nucleoactive nuclei at all, if we don't know that there is no nucleoactive nuclei, so if we do this only thing for, so for only copper, the thing will there only one copper is there, 2ni plus 1, so the number of signal appear is 4. Okay, this is the fine line. But as there are a nucleoactive nuclei, for nitrogen the I value is 1, for hydrogen I value is half. So you can see there are two active nuclei. Okay, so they will also split it. Okay, so total number will come like for total signal. Okay, number of copper for number of nitrogen for number of hydrogen. Okay, understood? Okay, now in the question they have specified something. Okay, okay, before going to that, let's calculate it. So if we calculate this, so you can find this will come around 4. This is, so 1, it is 5, and this is 2. 2 nitrogen, 2 hydrogen. Okay, this is 3. So come should come 60. But in the question they have specified something that NH protons they will not contribute. Okay, they will not alter the APR proton. Means suppose they are nuclear inactive. Suppose means after 2 nucleus the hyperfine splitting constant become negligible. Okay, then they ignore this part. So if you ignore this part, so only 20 lines will appear. Understood?